So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and at the moment I'm the interim director of NITheCS. Yeah? This afternoon, we have the big pleasure of having Professor Jonathan Schock with us. Jonathan is based in the Department of Mathematics and Applied Mathematics at UCT, where he's associate professor. But he's originally from Oxford, and he completed his PhD at the University. Sorry, I forgot. At the University of Southampton, yeah, back in 2005. Yeah? And originally, his research was mainly focused on string theories and quantum chromodynamics. Yeah? After his PhD, he traveled a little bit, and I think he's only one of the few persons I know who had positions on almost all continents. There is just one missing. Yeah? So he spent time in China, in South America, in Europe, yeah, and moved to UCT in 2013. Yeah? And today he will speak about some of his more recent interests, which is aspects of machine learning, and in particular reinforcement learning. Yeah? So Jonathan, we are really happy that you accepted our invitation and that you're here with us today. And before I ask you to share your screen, the usual reminder to the participants to please make use of the Q&A to ask questions or raise your hand, and after the talk or during the talk, we'll make a plan to give you the rights to pose your question in person. Yeah. So Jonathan, sorry, I always forget another reminder. After the talk, Jonathan agreed to join us for our canonical social event in Kumo Space. So if you are interested in chatting to Jonathan in a less formal environment, you're welcome to join us after the talk in Kumo Space. I will post the link in the chat, and your browser should have already gone to that page anyway. Yeah. So Jonathan, now people are here to listen to you, not to me. If you would like to share your screen, you're welcome to start your presentation.
Fantastic. Can you see the screen
yes,
now?
Perfect. And now it's in full screen. Fantastic. Thank you very much.
Wonderful. Thank you very much, Francesco, for the opportunity to come and talk to everybody here about this aspect of machine learning that I've been interested in now for a few years. Some of you may have seen a good amount of this. It's really going to be a very introductory discussion. So I'm very happy to have questions along the way. If anything doesn't make sense, if there are things that we need to talk about afterwards, that's fine. But yeah, please feel free to ask questions. So is this going to work? Okay. So the first thing I'm actually going to do is to pose a question to you. So I'm just moving some things around on my screen here. Is to pose some things to you to ask, why are you here? So this is actually a question I want you to think about. Why are you here watching this seminar at the moment? What's the reason for you being here? And I hope that the answer is that, you know, you presumably had some choices as to what you could be doing at the moment. You know, you could have had a nap, you could be getting on with some research, you could have been playing Wordle, but you chose to be here. And I'm not saying this just, you know, out of some egotistical sort of feeling. I'm saying this because you chose this because you decided that being here had some value. There was value in you being here, and there could be value in lots of different ways. It could be that it's, you know, it enlivens you and makes you happy to see interesting new things. It might be because you believe that watching a talk like this might lead you on to be able to do something else in the future, where maybe you can get into machine learning and join a company and earn money and put food on the table, or whatever it might be. But the point is, you made the decision to be here because you thought that being here had some value. And the reason I'm saying this is because that's really the fundamental idea about reinforcement learning. Reinforcement learning is about an agent, an artificial agent, which moves around in some environment and makes choices about its actions in order to move to states which it believes, I'll sometimes anthropomorphize, which it believes has value. Okay, and that's really going to be the fundamental idea of this this area of machine learning. The idea is you want to get a machine to solve some task, and the way it solves it is by having some set of rewards. We're going to define all of this in detail in a bit. And it decides upon its actions based on the direction it sees through this state space that's going to lead to it getting higher rewards, which means states which have more value. Okay. Okay, so a quick plan for this talk. I'm going to talk about where reinforcement learning fits into AI as a whole. I'm going to talk about some of the things that reinforcement learning can do and the sort of general basic idea. And then we're going to get onto the technicalities where we talk about Markov decision processes. And this is really the sort of fundamental language that we're going to use to define reinforcement learning. So then we're going to be able to define it. And then we're going to talk about some simple algorithms for how one can learn to interact in an environment. We're going to talk about some exact methods, things like value iteration. And then we're going to come on to some more recent advantage on some more recent methods, things like temporal difference learning in the guise of Qlearning, and then so-called deep Qlearning, deep Q networks, which are the application of deep neural networks to Qlearning. Hopefully all of this will make sense soon. And then we'll talk about a few of the recent developments and interesting directions that reinforcement learning is going in. Some references which I highly recommend. So Sutton and Bartow have the canonical textbook, and it's just called Reinforcement Learning. They actually put it for free online, although you can purchase the copy from bookshops. And it's an extremely readable textbook. So it's one that you can really sit down and tear through. It's technical, but it's not so technical as to be scary. You don't need a very strong computer science background. You need some, basic university level maths, but not a lot more than that. You can also find the Deep Reinforcement Learning Bootcamp on YouTube, and then 2-Minute Papers is a very nice YouTube channel which has short discussions about some of the recent developments in artificial intelligence. So the first thing that I want to sort of clarify is the relationship between different things which I think are often conflated. So artificial intelligence and machine learning, how do they fit into one another? What is deep learning? What is supervised, unsupervised, and reinforcement learning? So let me do that with the simple Venn diagram. Okay, so what we have here is it's an image. The central image here is taken from this archive paper, and what you see is, as a whole, all of this is artificial intelligence, and a subset of artificial intelligence is so-called machine learning. So you'll see that there are some things which are artificial intelligence which are not machine learning, and those tend to be things where you have a set of hard-coded rules for either formal logic or expert systems or these sorts of things, where the computer isn't learning from data. Okay, it's not learning as it goes along. It's got a set of rules already built in. So the subset of artificial intelligence that we're interested in is machine learning, where the machine learns, it's got some set of sort of meta rules about how to learn, but it's learning from data, and that might be data that you give it or data that it gets from interacting in an environment. Now, within machine learning, there are really 3 different areas, and there may be some overlap between them, and it's something that we happen to have defined. So there's supervised learning. And in supervised learning, one has a set of labeled data. So a simple example here, we've got a set of temperatures and the percentage of people outside based on those temperatures, and we see that it fits some sort of curve like this. But the point is here, the data set is labeled. You are given a set of data which says the percentage of people outside when the temperature is, let's say, 9.5 degrees. And what this allows you to do is to fit a curve to this data using, some simple mechanism like least square, the minimizing some loss function to do with the least squares. And it allows you then to make predictions about unseen data. So that is to say, okay, so there may be some data at 9.5 and 10.2, but this allows you to make a prediction about the percentage of people who will be outside when it's, let's say, 10 degrees. Okay. This is a simple made-up example, but that's the general idea. Okay. So then we have deep learning, and deep learning is a set of tools which one can use to solve all of these different problems. Now, generally, one wouldn't need to use deep learning to solve a problem like this. It's a very simple sort of regression problem. It's not necessarily a linear regression problem, but it's fairly simple. But what one might want to use deep learning, and what we mean by deep learning is the application of deep neural networks to these sorts of problems, to these machine learning problems. So you might get, for instance, a data set which is pictures of thousands of galaxies, where each of the galaxies is labeled, possibly with one label, for instance, just the type of galaxy, or possibly a number of labels, type of galaxy and some subtype, maybe the size of the galaxy. And what you want is to have a system which can take these images, pixel values, and learn from them in order to then see unseen data and make a prediction as to what the label of the galaxy that it's not seen before is. Okay. Then we have unsupervised learning over here, and we have some simple problem here where we've got a data set where there's no label. So the X and the Y axis here isn't sort of the feature and the label. This is just two features here. And you see each of these points is a data point in our set. And the question here is, can one find clusters automatically in this data? And of course, you could come up to this and you could sort of put a, some circle around here and a circle around here and a circle around here. But the idea of a machine learning problem would be to look at this data set and to make a prediction as to the probability of a particular data point being in one of these three clusters, given some new data point. So that's a sort of simple non-neural network approach to unsupervised learning. And then up in the top right corner here, we have an unsupervised learning example called a GANS, a generative adversarial network, which is a way of generating new data from old. In this case, generating pictures of people's faces. In fact, in this case, it's so-called celeb GANs, where the computer learns to generate images of people's faces, even though the system which is doing the generating has never seen a picture of a face before. If you haven't read up about GANs, I highly recommend it. It's a fascinating subject. And then we have reinforcement learning, which is going to be the subject of this talk. And then, of course, deep reinforcement learning, which is the application of deep neural networks to reinforcement learning problems. Okay. So my personal interest in machine learning, it's really twofold. One of which is how we can take machine learning and apply it to understanding human cognition and affect being essentially feelings and emotions, these sorts of things. And that is studying things like human attention, using the active inference framework, trying to look at consciousness. These are big questions, but I think, we have some interesting tools within machine learning to start looking at these questions. And then the other way around, my interest is, how do we use aspects of human cognition in order to motivate novel machine learning algorithms? So ideas of human attention, communication, offline learning, we might talk about that a little bit later, and saliency, to do with when one looks at a particular scene, what are the salient features? How do you bring that out? So I'm sort of interested in machine learning from these two directions. Okay. So where did reinforcement learning come from? So really, reinforcement learning is sort of the agglomeration of two different subjects. One is psychology, where we understand about how humans and other animals learn through trial and error, and the idea of secondary reinforcers, and I'm going to talk about that a little bit more later. And then optimal control theory, where there are ideas of value functions and dynamic programming, which we're going to talk about in quite a lot more detail. And although optimal control theory has some similarities with reinforcement learning, it's not really learning in the sense that we're interested. And then these two subjects came together into the guise of reinforcement learning, and with temporal difference methods, things like Qlearning, that gave rise to what we see as modern reinforcement learning. Okay. So before going on to studying reinforcement learning in detail, let's see what it can do. And what we have here is a simple application of an agent which is controlling this paddle at the bottom, learning to play this game. Now, the agent has information about the pixel values and the score that it has. And through trial and error, it learns what are the motions that it can do in a given state in order to bounce this ball around and break the blocks here and increase its score. So its reward is the score that it gets. And it learns the appropriate motions in a given state in order to take it to the next state that it sees as having value. And what we see here is that after some amount of time, it's able to do very well. But in fact, after twice as much time, in this case, 240 minutes of gameplay, it realizes, and when I say realizes, again, I'm anthropomorphizing, it finds that there's a sort of a shortcut, a way to solve the problem without having to do all the hard work. It can send the ball up to the top and solve the problem much more efficiently than maybe a good human would be able to do this. Now, the point here is that the rules of the game haven't been programmed into the agent's sort of mind. All it has is pixel values and reward, and it has to learn to associate a given action in a given state with having value to take it to a state which is going to bring it more reward. And it's simply through trial and error. It doesn't know anything about balls or computer games or paddles or anything like this, or object permanence. It's just doing it through trial and error. Okay. If you haven't seen the AlphaGo documentary, I highly recommend it. So this was a pretty big breakthrough in using reinforcement learning to play the game of Go. It's a game that originates in East Asia, is played in Korea and China and Japan. And the AlphaGo documentary tells you about how Google DeepMind really mastered this game. And it was a game that people thought was going to be impossible for to get computers to play at a level better than humans. It's got a far larger state space, much more complexity than chess. And so it seemed like a much harder challenge. But using reinforcement learning and essentially getting a computer to play itself again and again and again, and build up an understanding of the values of different states and the appropriate policy or what actions it should take in particular states, it was able to get to a level that not only could beat the average humans, but it was actually able to beat the world champion and really quite significantly beat the world champion. Indeed, what it was also able to do was in a particularly famous move called move 37 in I think the second game, the computer played a move which everybody thought that the computer must have some bug. It was a move that sort of confused all of the pundits watching around the world. But when Lee Sedol, who's the player here, the world champion, came to look at the board, he realized that the computer had actually found a move that no human would have thought of and opened up an entirely new realm of possibilities for the game. And I think in any sensible definition, this is the idea of creativity. It's novel behavior, novel actions that have value, and absolutely the AlphaGo algorithm was able to come up with a completely new strategy for this game, which no human had ever thought about before. So here we see another reinforcement learning system. So here, this agent has no physics programmed into it. It doesn't know anything about physics. It doesn't know anything about walking or movement. All it's done is it's rewarded for moving from A to B and tries again and again and again. And over time, it learns what are the correct actions to take in order to move it. So what we see here is that the agent, in this case, sort of humanoid or some animal like robot, is able to find the appropriate actions in order to perform a task without you having to program in the dynamics of motion and the dynamics of walking. And although it might look a little strange, it manages the task very well. Things like automatic driving, self-driving cars, reinforcement learning can be used there. Of course, you don't want to have cars running on the road, using trial and error from the start, but one can use it as a way to improve algorithms by finding what works and what doesn't when there's some 50-50 decision to be made, and it's able to feed that information back into the system, learn from any mistakes, and improve the system over time. Manufacturing too, anything where there are actions to be taken and something which should be optimized, reinforcement learning is really a very good way to go. And then finally, this sort of simple example, this is the so-called swing up cart pole. And the idea here is you've got a little robot on a track and it can move back and forth. And it's trying to balance this pole vertically. Okay, so it's going to move back and forth, and it's going to start off not knowing anything about what to do. And the feedback it gets is how much time it spends in some relatively vertical position. And I've actually sped it up a little bit because the video is a little long otherwise. But what you see is, the first time it's pretty terrible. Second time it's pretty terrible too. It doesn't seem to be managing the task very well, but each time it's getting more information about what to do. Still doesn't seem to be solving the task, but each time it's getting more and more information about the relationship between what it does and the states that it wants to be in. There we see that it spent quite a lot of time at the top, but it was spinning around very quickly. And now you see that it's starting to learn something about the movements back and forth, which keep it close to vertical. Seems to be doing a bit better here. And finally, after about, I think it's 15 seconds or so of experimentation, oh, it hasn't quite mastered it there. It's almost got it after one more attempt. It's going to have enough information to have mastered this problem. There we go. So now it's mastered it. Okay. And this was all done through reinforcement learning. Okay. So teaching rules is really hard. So for instance, that swing up carpole, you could certainly program in the physics of it and the momentum of the top and all of these sorts of things. And one could hard code in the rules for what to do in order to keep this thing standing vertically. But the point is that it's generally very hard to program in those rules, and it's much easier when it's possible to let the system learn for itself. Okay. And that's really what all these things have in common, is that they are about getting a system to interact in an environment and learn to solve a task, to perform some task, which is well defined by the programmer. This is extremely important. The reward structure must be defined by the programmer, and is able, through trial and error, to learn how to do this. So in a sense, one might ask the question, why is this not part of supervised learning? The answer is that you never instruct the agent what to do. So if it's tried something, you don't say, oh, no, you should have done this instead. All you do is to say that was a good thing or that was a bad thing. You managed to solve the task, you didn't manage to solve the task. You got this much reward, positive reward or negative reward. And it uses that simply to move its actions in a particular direction, which over time will increase the amount of reward that it gets. Okay, we need to formalize things a little bit now, so we're going to get onto a little bit of maths. And this comes from Richard Bellman in 1957, who was one of the people who was really pushing ideas of optimal control theory and dynamic programming. And he introduced the idea of the Markov decision process. Okay, so this is a Markov decision process. So what do we have here? So this diagram here, well, I seem to have lost my mouse now. So the blue circles here are states. Let me see if I can get the mouse back. Sorry. Okay. So the blue circles here are states. States of some system, it's not defined what the system is. So we've got state S0, state S1, and then these two are squares because they're what are called terminating states. So once you've got to these states, the game is over, whatever it is finished. From state S0, there are a number of actions you can take. You can take action A1, A2, or A3, and probabilistically, they will take you to different states. So for instance, if you take action A1 in state S0, then with probability 0.2, you will end up back in state S0. With probability 0.3, you will end up in state ST1, and with probability 0.5, you'll end up in state S1. Okay. Then we have here the rewards, and of course all of this is defined by the programmer. It's dependent on whatever the game or the system or environment is. Here we have some rewards, and here's a reward of -3, here's a reward of +0, here's a reward of +5. So a Markov decision process is made up of a set of states and actions and rewards, where the rewards are defined by taking in the state that you're in, the action you take in the state that you end up in, and a set of probabilities, transition probabilities. What is the probability of ending up in state S prime, given that you are in state S and you take action A? Okay, so this is the idea of a Markov decision process, but we need to put something on top of this. And what we need to put on top of this is a policy. And a policy says, what is the probability that you will take action A, given that you're in state S? Okay. And that's going to be the thing that the agent wants to learn over time, essentially. There are different ways of doing this, but it wants to learn what is the optimal policy? What is the policy which over time is going to get me the highest rewards? That's how you program it. Okay. And it may be that you define the problem precisely through the policy, or it might be that you define the problem through the agent finding out which states have value, and then from that you can infer a policy. And a policy can either be probabilistic in this case, where the policy is the probability of taking action A in state S, or it could be deterministic, which says, given that you are in state S, what is the action that you take? Okay, so there are two ways of doing it. Okay. So, of course, the policy depends on what it is that you're aiming to do, and we need to define that very carefully. So this is really the framework of reinforcement learning. You have some agent, which I've drawn here as a brain, which at time t takes some action. Oh, well, it knows that it's in some state, st, and it's got some reward, rt, and based on its policy, it chooses some action, at. That action goes to the environment and feeds back there and alters the environment in some way. It takes it from some state st to some new state st plus 1. And that information is fed back to the agent along with some new reward. Okay? And this is all you need in order to think about the reinforcement learning framework. Of course, what needs to happen now is that based on this new information, the brain, the agent, needs to update its policy, needs to update its understanding about the values of being in given states, such that it can solve the task. And we need to define what we mean by solve the task. I see there are some questions here. Oh, you cannot see the cursor. Is that still the case, that you can't see the cursor?
No, we can see the cursor, but I'm not sure how crucial it is, because I think, yeah, okay. I think it's okay.
Okay, sure. Let me know if anything isn't clear, and I'll try and not utilize that too much. Can I annotate? No, I'm not going to do that. Okay, very good. So one question you might want to ask first is, does the world seem to be like a Markov decision process? So, the Markov property tells us that the only thing which is important in terms of the transition to the next state is the current state. But of course, that's not always the case. If you're playing chess, for instance, it matters with an en passant move as to exactly what happened in the past. Or in terms of castling, it matters what happened in the past. You can't just look at the board and know what are the possible actions, the possible next states. You need to have some information about what has already happened in the past. But what you can do is you can augment the states with some information about what has happened in the past. It's like adding a memory module to the state. So for instance, if you know that you have already moved the king, you can include that as some state information, and that then says that you're not allowed to castle. Okay. The world also has a lot of information which is hidden from you as an agent. But it's actually possible to take the idea of a Markov decision process and extend it to what's called a partially observable Markov decision process, and you can still perform reinforcement learning tasks in partially observable environments. Then, of course, the world is continuous, whereas it looks like that Markov decision diagram was discrete, but there are ways to extend this to the continuous state. Okay. So what are we trying to do? So let's think about this. So we can define a total reward of some path through the Markov decision process, and that's denoted tau. As the trace. So G here is the total reward, and it's simply, as I move from one state to another, what rewards do I pick up? And there's no reason, incidentally, that I've gone from R0 plus R2 here. It should just be R0 plus R1, etc., etc. It's just the rewards that I pick up along the way, up to potentially some horizon. It may be that the game carries on forever. It may be that there's some finite horizon and the game ends at t equals h. But the total reward over time is simply the addition of all of the rewards as I step through. Okay. And we can think of the value of being in a state in very general terms as the expected rewards that I can pick up from moving from this state. So I'm in some state at the moment. And the question is, how valuable is this state? And the value of this state is simply the expected rewards that I can pick up moving into the future. So the idea of Pavlov's dog, what it was actually named, the salivation of the dog was actually called psychic secretion, which I think is a rather wonderful term. And the idea there is that food for the dog was the reward, but by associating ringing a bell with the later appearance of food, the bell becomes something that has value. Okay, the bell on its own isn't a reward, but the bell has value because the dog then knows that if you ring the bell, something good is going to happen in the future. So the state of ringing the bell leads to a state where there is a reward, and therefore the state of the bell, the ringing bell, has value. I'll come on to the question from Rianne, I think, after I finish the talk, but it's a fair question. Okay, so here we see that the bell is something that has value because it is associated with a future state, where there is some reward. So we're going to start off in a really simple environment. It's called a grid world, and it's something which is sort of used to explain reinforcement learning concepts. And the idea here is that you start off in some state here, you move in discrete steps, and you can move through all of the blank squares here. This is some square which I've defined as one which you can't get in, you can't enter. And there are two terminating states here, one which, once you arrive here, any next move you make is going to end the game and you get a +1 reward. And the same thing here, once you arrive here on the next move, you end the game and you get a reward of -1. Okay. And so the question here is, if you start here, what's going to be the appropriate policy to move around the board and to get to the +1 state? That's the aim of the game. And looking at this is very obvious what's going to happen, or the solution to the problem is very obvious. But the question is, how can we get a computer to learn this? Okay. The first thing that we want to do, though, is to ask the question, well, it's clear that we defined previously the total reward starting in some states at time t = 0 is simply the sum of all of the rewards. But if all we want to do is to find the states which increase the expected future rewards, well, it could sit in one state for ages, not getting any reward, knowing that in the future it can pick up rewards along the way. But what if we want the system to solve the maze, for instance, in a short time? What we can do is to introduce what's called a discount factor. And the discount factor here is this gamma, which is a number between 0 and 1. And the smaller the value of gamma, the more rewards which are picked up in the future or expected to be picked up in the future are going to be discounted, and they're going to become less important. So what you're going to want to do is to get to future reward state as quickly as possible so that this gamma to the t is as large as possible. Okay, because the longer you wait, the less important it's going to be. Okay. So we need to define here what it is that we want to tell the agent to do. So we want to find the policy pi, which maximizes the expectation of the discounted rewards, future rewards, conditioned on policy pi. And this expectation here, it's an expectation because, remember, the policy itself may be stochastic. That is to say, the policy simply says what is the probability of taking a given action in a given state. And secondly, the environment itself may be stochastic. So there may be some transition probability between one state and another. So this is an expectation value where really you're going to have to sum over with a weighted set of probabilities over both the policy and the transition probabilities. So this is what we're trying to do. We're trying to find the policy which maximizes the expected discounted future returns. Okay. So we need to formally define the value of a state. We haven't quite defined this. And the value of a state is simply the expected future returns from being in a given state, S0 = S, conditioned on a particular policy. So what that tells us is that the value of a state is only well defined given a policy. Okay, if your policy is I'm just going to sit here forever and do nothing, and you're not sitting in a state that gives you reward, well, the value of that state is 0. Okay, so a state is only valuable if you have the action which takes you to high reward states. Okay, so this is how we're going to define the policy, to define the value of being in a state, and it's dependent on the policy. This doesn't say whether the policy is good or bad. It just says that given a policy, I can now define the value of a state. It's just the expected discounted future returns starting in that state. So this seems a little bit circular. So we see here that the policy, if we define some policy, then that tells us what the value of being in a state is. But we also said that what we're trying to do is to essentially move through the highest value states. So we want to find the state which has the highest value from the one that we're in at any one time, which says that the value of a state informs what the policy is. So this seems circular. It sounds like this is a bit of a problem. But in fact, we're going to be able to find methods whereby we can find the optimum policy by iteratively tuning the values. And we'll see that in a moment. Okay, so let's take a simple example and just say, given that we actually know what the optimum policy is, the optimum policy is either to go up here, oh, sorry, you can't see this, is to move up from the start and then right and then end up on the +1 square. Or of course we could go right and then up and then right. Either one is fine. So given that we know that, what is the value of each state? Well, the value of each state is just +1 if there's no discount. Okay, because we know that given the optimum policy, the one that will get us to the +1 state, every state has value +1 because, well, we're eventually going to get to the +1 state and there's no discount factor. Now, if we add in a discount factor, but we still know the optimum policy, well, now we know that the value of the states, let's say we've got a discount factor of 0.9. So the value of states further away from the state where there is a reward are discounted more and more and more. So this green state now has value 0.9 because on the next move, it can get a reward of +1. The one to the left of it, you've got to discount it twice in order to get to that state where there is a reward of +1. Okay. So in this case, the transition probabilities are probabilistic. But what happens if that's not the case? So what happens if we define the game now such that, let's say we're in this square that we're pointing out with the arrow. If we try to move to the right, if we take the action which is move right, then only with probability 0.7, I've said left here, but it doesn't matter. So with probability 0.7, we move in the direction that we want to move in. And with probability 0.1, we move to one of the other three directions. And in this case, if we try to move up, then we'll end up back in the same square. Okay. So now the formula would tell us that the value of being in this state, S22, would be 0.9, which is the discount factor that we've defined here, times 0.7 of the value of being in state S32, we haven't defined what that is necessarily yet, plus 0.1 times the value of being in state S12, etc., etc., etc. So it looks like this is simply linear algebra, but of course this is under a particular policy, and what we're trying to do is to find the policy which maximizes the expected future returns. Okay. So what do we want to find? We want to find, given some policy, we want to find what are the values of the states. And then we want to compare that with other policies and find the policy which optimizes those values over states. Okay. So our policy is going to be, and this isn't always going to be the case, but generally our policy is going to be, let us move into the state which is next to us in some sense, in state space, that has the highest value. So you're always looking around and trying to move to the highest value state. Okay. So let's see how we can define this in iterative fashion. So this is what we defined before. So the value of being in some state S under a policy was this expectation. And we can actually expand this to take out the reward from moving from state S0 to state S1, plus now we've got the sum t equals 1 to h, etc., etc. But we can actually rewrite this, the second term. I've been a little bit sloppy here about the expectation value, but one can do it all in a slightly less hand-wavy way when you put in the transition probabilities. But essentially, this is the expectation now of the reward plus gamma times the value of being in state S1, because remember the value is just the sum, the expected future returns from being in state S1. Okay. So now we have a relationship between the value of being in state S and the value of being in state S1 in this case. Okay. And we can write this now as a sum, so rather than the expectation value, because remember this state S1 was the state that the policy pies told us we were going to get into under the policy. We can write this out now explicitly rather than the expectation value, actually summing over the probabilities, where here we have the probability which is the policy and the probability which is the transition probability. And this gives us the famous Bellman equation. The Bellman equation is sort of the fundamental equation of reinforcement learning, which says that we have some iterative relationship between the value of one state and the value of all other states. The Bellman optimality equation says, okay, well, what if we wanted to find the optimal policy? The optimal policy being the one where you're going to actually maximize the expected future returns. So the optimal policy is the one which takes the action which maximizes this term on the right. Okay, and pi star is generally defined as the optimal policy. Okay, so how can we calculate these optimal policies? So the algorithm that does this is what's called value iteration, and this is the algorithm for value iteration. We're going to start off with iteration 0. So what I've got here is v0 star of s. The 0 is sort of the iteration number. So on the 0th iteration, we set all states to 0, the value of all states to 0. On the next iteration, we calculate the values by using the Bellman optimality equation. Okay, so what that says is the new values are going to be the expected, taking the maximum action of the expected future returns, which takes into account the real rewards. So the reward here is actually the reward that you would find if you moved into some new state, plus the values from the previous iteration, which of course in this case is 0 at the moment. Okay. And you do this again and again and again, and what you'll find is that you converge, this is provably convergent to the optimal value. Okay, the optimum set of values. And then once you found the optimum set of values, the policy, the deterministic policy just says, always take the action which moves me into the highest value state. Okay. So let's see this in action. Okay, so in the Gridworld example, so the 0th iteration, we just set all values of all states to 0. In the next iteration, we find v1, where the 1 here is the sort of first iteration. We calculate here this expression, we maximize over the actions, but of course the values here from the previous iteration were all 0. So the only states here which are updated are those where you will actually get a reward. And of course the reward from the top right is a +1, and the reward from the one down is -1. Okay, and in fact, those ones are deterministic, that once you're in those states, you will necessarily get a reward of +1 or -1. Okay, so we do this again, and now what we find is that the information from those propagates backwards. So now the states which can reach those states, which we now have some value, are themselves updated, because we see that we can move from them into a state which has value. And we can do this again and again and again, and we propagate this information back from the rewards all the way back until we find here a convergent set of values. And once we've found these convergent set of values, we can now calculate the policy, where the policy simply says, okay, if I start in this state on the bottom left, now I'm going to move into the state that has the highest value. Which one is that? It's the 0.34. Then I move to the state with the highest value from there, the 0.45, etc., etc. Now you might ask, it looks symmetric. Couldn't we just move right from the bottom left state? Well, we've set this up in the system where the transition probabilities are not deterministic, they're stochastic. So this state here with a value of 0.49, although of course, the optimum action would be to move up, there's some probability that you might accidentally move to the right and end up with a reward of -1 from there. Okay, so in fact, because of the stochastic property of this particular Gridworld setup, one would want to avoid getting anywhere close to the state with rewards -1. Okay, how are we doing for time? Okay. Okay. So in all of this, what we actually needed to know in order to perform these calculations, and if we go back to this here, so this value iteration, one of two things we needed to know. We needed to know explicitly what were the transition probabilities, these probability of moving into state S prime, given that you're in state S and you take action A, and we need to know the rewards. Okay, and that's not always the case. Okay, so knowing these two things says that we know the model explicitly. And in general, you don't know the model explicitly. The agent is simply exploring and it doesn't know what the transition probabilities are, okay? So although I've set this up as sort of the first algorithm to try and find some policy in an environment, this isn't actually what one normally does. This is simply the idea of dynamic programming to find some policy given that you know the model. Now, what happens if you don't know the model? So what we can do is to sample from the environment. And I think it's a good thing sometimes to anthropomorphize in these situations. So what one can say is, let's say I'm in some states and I don't know anything about the transition probabilities, but I've got some policy, and the policy may be a random policy. But I'm going to start off in this state and I don't know what the value is, but I'm going to find out what the value is based on my policy. So what do? I start off in this state and I simply wonder. I move through the environment based on my policy and I pick up whatever rewards I get. And then when I get to the end, whatever the end is, I can propagate that information back to the state that I started in and say, well, now I know based on my policy how valuable that state was. Okay. And then if it's a stochastic environment where there are transition probabilities, or if my policy itself is stochastic, I can do it again. I can start off in that state again, and I can move through the environment, and it might take me on a slightly different path. And I'll again propagate that information back and update the information that I have to say, well, now I've learned some new information. Okay, now I know that this state is more or less valuable than I thought, and I might want to do some weighted sum over all of the different paths that I can take from there. And then I can start on a different state. Okay, and I can do what's called a Monte Carlo search through the environment and update the information to tell me how valuable that state was that I started on. Now, in this case, I'm sampling from the environment. I don't actually need to know what the transition probabilities or the rewards are. The environment tells me which new state I'm in because I tell it what action I want to take. And it also tells me what rewards that I get. Okay, so this is a so-called Monte Carlo algorithm for finding the values of states. But it's also sometimes sort of a long-winded way of doing it. So we don't always want to start in a state and move all the way to the end of the game or whatever it is in order to propagate the information back. Maybe we want to do this in fewer steps. Okay, I'm not going to go through the details of this slide. Okay, so the Monte Carlo method here. In fact, in general, what one does is we adapt our notion of the state value to what's called a state action value. Okay, so a state action value is, rather than V of S, it's Q of S and A, which says, given I'm in state S and I take action A, how valuable is this pair of states and actions? Okay, so we can actually define a Bellman optimality, equation for the Q values. So now the Q values are no longer maximizing over A because the Q value here for an optimum policy pi star is defined for some state and taking some action, and it looks very similar. Okay, it's a similar recursive equation. Okay. Details of this don't matter too much, but essentially the Q value is just how valuable is it to take action A given that I'm in some state S based on whatever policy pi I have. And this is the Bellman optimality equation, which says that I am finding the policy which optimizes, which increases the possible Q values of all states. Okay. So for instance, in this case, we'd have 4 times as many Q values as we had simple state values. Okay. So I've actually already explained what happens here. To calculate, in this case, the Q values, I start off in some state S and take action A and follow whatever policy I have. I repeat this again and again and again, and I can average the returns that I get, and I now update the Q value that I had. Okay, and there are various problems with this, but the general idea certainly works. So now we can do something rather than stepping through the entire path through the state space. I wouldn't look at what I've written up here yet. I'm going to explain it again in sort of anthropomorphic terms. So let's say I'm in some state S, and I think I know how valuable taking action A is in some state S. So I've got some numerical value. Let's say I think that being in this state S and taking some action A has a value of, let's say, 10. Now I can try that. Let's say I now take that action and I end up in some new state and I get some reward. And if the reward is really high, let's say there's a reward of 100 for arriving in that new state, having taken this action, I can propagate that information back, now not all the way down the path, but just one step back. And I can tell my former self, actually, you were wrong. You had underestimated how valuable that state action pair was. You thought it was only worth 10, but actually I've just discovered that there's a really big reward rate waiting for you. Okay, and you should learn to update this Q value a little bit to take into account the fact that you might end up in a really good state if you take this action. Of course, it's probabilistic, but you can propagate that information back and update the Q value. And this is what's called Qlearning. So now let's look at this algorithm. So we start off with some arbitrary set of Q values, just some random set of Q values for all state action pairs. Let's choose some state, initial state S, and we choose an action A from the state S using what's called an epsilon greedy policy. Sorry, that should say an epsilon greedy policy, not epsilon greedy Q value. So epsilon greedy says, most of the time, I'm going to take the action which I think is most valuable, given that I'm in some state S. But some small percentage of the time defined by a parameter epsilon, I'm going to sample randomly from all the other actions that I can take. Okay. So I choose one or the other. Most of the time, I'm going to take the action which I think is most valuable. Some of the time, I'm not. And this is what's called the explore-exploit trade-off. I really want to exploit the information that I have, but I also want to explore because maybe there's some information out there that I haven't taken into account. I take that action A that I've chosen, and I move into the new state S prime, and the environment returns to me some reward. So the target, what I call the target, is the reward in the next state plus gamma times the value that I believe is in the next state, which says, you know, how valuable do I think it is moving from this next state onwards. And I maximize over the actions that I can take in the next state. Okay. I then go back and I update the Q value for the original state action pair with some weighted sum, 1 minus alpha times the Q value that I thought there was originally, plus alpha times the target, which says, given some learning rate alpha, I'm going to shift myself towards what I discovered in the next state. Okay, I discovered some new information about the reward. I'm going to propagate that back and update it. Okay, and I can repeat this going through all the different states until I reach some terminal state, and I can repeat this for different starting states S, and I can do this over and over again, and eventually again I will converge to some optimal set of Q values. Okay. Sorry, I should say here, so what we've done here is we have simply found the Q values which are associated with some epsilon greedy policy. Okay, so we're going to eventually converge on the correct set of Q values because we are going to pick up information about the rewards. Okay. So it sort of sounds like Q value solved all of our problems. We no longer need to go all the way to the end of the episode. We can just take a single step, propagate that information back. And of course, there are ways to do this where we take some middle ground. We can move 2 steps into the future where we're going to get a little bit more information, but it might take us a bit longer, and we then propagate that back. Or we can go 3 steps into the future, or we can go multiple steps and sort of take some weighted average, weighted sum of the different pieces of information and propagate them back. And this is using something called an eligibility trace, which has actually some interesting analogies of what really happens in the brain as we learn. One of the problems with this, though, is that what we need here is what's called a Q table, okay, which is just a lookup table. So we've got a load of states and we've got a load of actions that we can take. And depending on the game, so for instance, Tetris, there might be an enormous state space. So Tetris has a state space of roughly 10 to the 60. Okay. It's, you know, it's completely infeasible to fill up that state space and get the information to have solved the game. Okay. There's a way to do that, though, which is to find some approximating function for the Q value. Okay. What we want to do is to approximate the Q value. And what that allows us to do is both it allows us to, in some computationally feasible way, store the set of Q values using something like a neural network, and that's what I'll come on to in a moment. It also allows us to generalize Q values on state action pairs that we've never seen. Because, of course, we might want to use some information about a state that we have seen, which is maybe similar to a new state, utilize that to guess what the Q value might actually be. And so, one way to think about this is that we could use some set of basis functions, some finite set of basis functions, fi on s and a, and those are predefined. And then we've got some set of parameters theta, where the theta is the thing that we're going to update to improve, to converge on some optimum Q value. Okay, so now we might have some far smaller set of parameters that we have to update than the entire Q table. Okay. So in fact, there's a clear way to do this, an obvious way to do this, which is rather than using a sort of set of basis functions like this, what we actually want to do is to set up a neural network. So I'm not going to go into the details of neural networks. I can discuss that another time, but essentially a neural network is a universal function approximator. Okay, and depending on the size of the network, it's going to approximate the function with some accuracy, some given accuracy. But essentially, you can think about it as some highly parameterized function with some set of parameters which are the weights of the nodes in the network, and the input is potentially going to be the state and the action value, and the state might be some set of pixel values in a game, for instance, and the output is going to be the Q value. Okay. So remember in Qlearning, what we have is a target, which is the thing that you have discovered on moving to the next state. And what we want to do is to move our Q values towards the targets that we discover. So if we have some parameterization of Q given by, for instance, a neural network, given by some set of parameters theta, then what we can do is we can update the thetas by moving in the direction of the steepest gradients of the difference of the function, which is the difference between the Q value that we had and the target. Okay, what we're trying to do is to find the minimum of this function. We're trying to move Q towards a place where we never need to update the Q values, because the value of the Q values is the values of the targets that we find. So we're trying to find the minimum of some function, which is this this function of Q minus the target squared. Okay, so we're simply going to move using some learning rate alpha in the direction which minimizes this. And by doing this, we can actually use a neural network to optimize our Q values. And this is so-called a deep Q network. We use deep learning to find the Q values. I'm aware that I'm pretty much out of time here. So there are many sort of different instantiations of this, and the idea of this deep Q network, the DQN, was used famously on a set of Atari games, these computer games, where for a large number of Atari games, it was actually able to outcompete humans by some considerable margin relatively quickly. So-called double DQN, which uses another set of neural networks on top of the DQN, was able to outperform that. And in fact, so this image that I have here is now fairly old. And in fact, all of the games we can now solve with superhuman performance using different versions of a DQN and what are called policy methods. And I'm not going to have time to go through policy methods, I think. But the basic idea is that rather than trying to approximate some Q function and optimize for the Q function, we actually try to optimize for the policy explicit. So here you might have some neural network where what comes in is the state and the output is the policy. So the probability based on the parameters theta in the network of the action given the state. And you might have some set of actions which are the output. And what you want is to move in the direction of the policy which optimizes the rewards that you get over time. Okay, I'm going to skip this. So various extensions to this are things called, for instance, random network distillation, which uses the idea of curiosity. So in all of this, there's sort of the agent is moving in the environment in some fairly random fashion, but using random network distillation, you can use the idea of curiosity for the agent to try to move into states that it has less information in than other states. So it actually actively says, okay, I want to move to this state because I have very little information, or I have very low certainty about the reward structure or the transition probabilities of this particular state. And using so-called random network distillation, they were able to do much better than any of the previous algorithms to solve one of the particular Atari games, which previous to that had been extremely difficult to solve. One can use ideas called world models, where essentially the agent has its own model of the dynamics, which it updates through trial and error. And it can then utilize the world model in order to make predictions about policies. And so there are all sorts of interesting aspects of causality, for instance, using world models. So this was some work by Jürgen Schmidhuber a few years back, is absolutely fascinating. One other thing that you might think about, so with the games that I showed you before, clearly when you see a computer game, you have some information about the way the world works, which you can use to start off the game. You're not starting from a blank slate. And so the idea of transfer learning within reinforcement learning is the idea that you take some skill, some set of information that you have from previous experience with other environments, and how do you transfer that over to a new environment? And it's a really difficult problem. Everything that I've spoken about here has been so-called single agent reinforcement learning. And there's a whole world of multi-agent reinforcement learning where the agents can communicate with each other in different ways, either competitively or cooperatively. And it's a fascinating area. So there's an organization here in Cape Town, InstaDeep, with whom I actually supervise a few master students, and their focus is in fact on multi-agent reinforcement learning. So all of their research is in that direction. Worth having a look. This again is actually a few years old now, but OpenAI's Dota 2 agent beat the world champions at this, what seems to me to be an extremely complex game, and was able to smash the world champions. And I think, yes, on that note, I'm going to end. So this is a paper which is worth a read. So-called reward is enough, which is saying essentially you don't need to program in any complicated feature engineering or dynamics. Having a reward structure is enough to solve extremely complex games, and that really is the fundamental idea of reinforcement learning. So I think I've gone a little bit over time there, but please feel free to ask any questions, or I guess there'll be a bit more of a chat later on in a different environment. So thank you very much, everyone.
Yeah, thank you so much, Jonathan, for a very nice overview of reinforcement learning. That was really great. Thank you very much. I see that we have a few questions in the chat. And sorry, Ilya, if I don't respect your job. And there are a few questions by Rian de Jong. And if he's still here, I'm more than happy to allow him to ask his question in person, and then we have a question by Zurab. Rian, you are on the panel. You're welcome to ask your questions.
Thank you, Francesco, and thank you. It was a very interesting speech and nice introduction to reinforcement learning. I appreciate that. I've got a couple of questions. Obviously, one would like to use these kinds of techniques in business as well. And typical business problems are characterized by quite complex problems. You can have many states, actions, the transitional probabilities. Usually you have great difficulty to even estimate. And in this Markov decision process structure, I'm not so sure. Well, maybe I must ask it like this. If I'm confronted with a real problem, like maybe making money with a trading strategy or so on, which of course will give me rewards if I do the right thing. But how should I approach it? Is there some other magical recipe? I've listened to talks before on neural network learning, convolutional networks, and then when I ask a practical question like this, the guy tells me, well, 80% of getting a good answer is to structure your data correctly for this deep learning neural network. Now, in this case, when you deal with real world problems, I think the question is, what's the effort to get the states and the actions and the structure of the problem right, so that you can actually get results?
Sure. So I think one thing which is maybe a missing perspective, and this isn't sort of your missing perspective. I think often people think about it like this: is that you don't need to define formally the Markov decision process. So long as you are able to have the agent interact in the environment, and maybe that's, I don't know, buying shares and selling shares, whatever it may be, and as long as there is feedback, there is reward coming in, that's all you need. So, the transition probabilities, that's out there in the world. The dynamics just happens. And the idea then is that you can say, okay, well, I want the agent to make actions, and based on those actions and the feedback, to update its policy or update its belief in the values of particular states. So in a sense, while, for supervised learning or something like that, it's extremely important to, get your data set exactly right so that it can be fed in so that the system can learn. In a sense, that's not as necessary in this case. What is necessary in this case is defining your reward structure really well. And I'll give you an example. So we saw at the beginning, there was an animation of these things sort of moving along, walking along. There was a situation where the programmers wanted to find out how an agent, which was a four-legged agent, could move from A to B, moving its legs as few times as possible. Or actually, I should say that differently, having its feet on the floor for as little time as possible. And so that seems like a well-defined problem. And what they wanted to find was whether it could sort of jump, a long distance. And the agent found that there was a solution whereby it flipped itself onto its back and it shuffled along on its back. Okay, so it solved the problem that the programmers had asked for, just not in the way that they were wanting it to. And the reason for that is because they hadn't defined the sort of constraints or the reward properly. What they should have defined was, with the orientation like this, so there's some reward for keeping an orientation the right way around rather than the wrong way around, then try and solve the problem. So the point really is that what is important is defining the reward structure properly. Okay, in terms of using this sort of thing.
But that could be complicated, I guess. If you have a kind of a problem that is reasonably complex.
Well, it depends. I mean, often the definition of the problem itself encodes the reward. So, for instance, something like chess or Go, although they're incredibly complicated games, the reward structure is incredibly simple. In yes. Go, you get a reward of +1 if you win the game, 0 if you draw the game, and -1 if you lose the game. So, there you've got a very simple reward structure. But certainly reward shaping can really help you to solve a problem more or less efficiently. In terms of applying this in the real world, for instance, to making money, I have to admit that this is something that I sort of stay away from. I think I have my own particular pessimistic view of using machine learning to make one's fortune. There's a lot of people trying this, and one might be able to make some sort of epsilon gain. But I think it's a really hard problem. If it wasn't an incredibly hard problem, then the structure of the stock market and the structure of the financial markets would themselves change in order to make, to change the problem. So there are certainly people who do use reinforcement learning for trading strategies. So it's, it's certainly something that people look at, but it's not something that I've looked at personally.
But thank you for that. I think that answers my question.
Great.
Yes. Yeah. Thank you.
Sure. Pleasure.
And Jonathan, Zurab Janelitste raised his hand. Zurab, please, you're welcome to ask your comment or question or make your comments. Yeah.
Thank you, Francesco. Thank you very much, Jonathan. It was a very, very interesting talk.
Thank you.
To be honest, I followed, I think, quite well the first half, and then the second half I didn't follow very well. Okay. And I think where I got lost was perhaps that you could help me with this. So at some point you showed us a diagram with arrows and states as nodes and so on, right? So how does that link up with the second half of the talk? So is the machine going to draw this diagram by itself after experience, or
this one here?
So how does that diagram? How is that diagram generated?
Perfect.
From trial and error. Yeah.
No, that's great. So in general, the diagram will not be generated. So this is to say, this is the type of problem where you need to move around some environment where there are states and you need to take actions, and there are transition probabilities and there are rewards that you pick up. So the canonical example of the type of problem that you would want to solve is a problem which is defined as a Markov decision process. So for instance, a game of chess, modulo, en passant, and castling is itself a Markov decision process. And so the fact that you can define it in this way, where there are well-defined transitions, there are rewards, there are actions that you can take in well-defined states, that's enough. So you don't need to write down this diagram in general ever. One can do so. There are ways that you can do it. But this is simply to say, this is the type of problem that one is trying to solve. It's a problem which is defined in terms of states and actions and rewards and transition probabilities.
Okay.
Does that
great.
answer the question?
Yeah, it answers the question. Thank you very much.
Sure, thanks.
Thank you. Ilya, do we have other questions in the Q&A? Or please, if there are other participants that would like to comment, please just raise your hand and we will make a plan.
I don't see other questions. There is just a comment from Rian that maybe the successes in the money making is never published.
Yeah,
That's
that sounds like a good strategy.
Probably be wise. Yep.
That sounds like a good reward strategy. Yeah. Okay, wonderful. Then Jonathan, if there are no more questions, thank you so much. And for your time and for preparing a very nice talk that I think everybody enjoyed. Thank you so much. And a quick reminder to everyone, please, if you have 10 minutes and would like to interact in a less formal environment with Jonathan, just join us in Kumo Space. The link is in the chat, and your web browser should have opened on the page anyway. Yeah. So thank you very much, everyone. Please remember that next Monday is a public holiday, so we won't have a colloquium unless you miss it so much, and then in that case we can make a plan. Just let us know. No, but by default there won't be a colloquium next Monday. So thank you very much, Jonathan, again for your time, and we will see you in a few seconds in Kumo Space.